All right, today we're going to break down a really fascinating new blueprint for AI safety. It's called CAST. Now, it's built on some pretty heavy-duty math, but don't worry, we're going to zero in on the three most important ideas that make the whole thing work. So, let's get right into it.
This is pretty much the question in AI safety right now. You see, we've moved way beyond AIs that just write text. The most advanced models out there can now actually use tools. We're talking executing Python code, for example, to directly mess with the world. And that just fundamentally changes the whole game. A mistake is no longer just a weird sentence. In really high-stakes fields like automated financial trading or scientific computing, a single bad action could have massive, and I mean massive, real-world consequences. The risk has officially left the chat and entered reality. So this is where CAST comes in. It stands for Certifiable AI Safety Theory. And instead of just, crossing our fingers and hoping an AI behaves, CAST builds a mathematical safety net around it. It's a system that's based on verifiable proof, not just flimsy promises. So how does it actually work? Well, let's start with the first big idea, which is all about defining what safe even means, but with mathematical precision. CAST calls this the safe zone. Okay, so at its core, CAST takes this kind of fuzzy idea of safety and turns it into a hard-edged geometric shape. The best way to think about it is like a digital playground. This shape, which technically is called a convex safe set, basically draws the fence for that playground. It contains every single possible action the AI is ever allowed to take. And here's what that looks like in practice. The AI comes up with an action it wants to take, right? And that action gets plotted as a point on this graph. If that point lands inside the nice green safe zone, great, it gets the green light. But if it lands outside, like that red crossover over there, the system blocks it instantly. No questions asked, no exceptions. So a simple way to think about it is this. Instead of trying to psychoanalyze the AI to see if it's good, CAST just checks the address of the action it wants to take. If it's in the pre-approved safe neighborhood, welcome in. If it's not, access denied. It's really as simple as that. Okay, so we've got our safe zone, but if you have an exclusive club, you need a bouncer at the door, don't you? And that brings us to the second key idea, what we're going to call the AI bouncer. This bouncer is technically called a runtime gate, and it's basically the muscle of the CAST system. It's the active enforcement. Before any action can actually happen, it has to get past this gate every single time. Let's break down how the bouncer does its job. First, the AI proposes an action. Then, a monitor gathers up evidence to prove that the action is safe. And this evidence basically acts like a safety certificate. The gate then verifies this certificate. Only after that verification is the action released. And if it fails the check for any reason, it gets dealt with on the spot. And dealt with can mean one of two things. The system can repair the action, which means it mathematically nudges it just enough to get it back inside the safe zone. Or it can replace it entirely with a pre-approved, totally safe dummy action, which could be as simple as do nothing. Either way, the key is an unsafe action never ever gets through. So we have a safe zone and we have a bouncer. But how does that bouncer know it can trust the AI's proof of safety? I mean, what if a really clever AI tries to forge its safety certificate to sneak a bad action past the gates? This is where our third and final pillar comes in. The whole system's security isn't based on trust at all, not one bit. It's based on a super strict set of rules called a capability contract. You can think of it like the unhackable terms and conditions for how the AI is allowed to behave. And this contract is what makes the whole verification process cheat-proof. And these rules are absolutely non-negotiable. State freeze means the AI has to hold perfectly still while it's being inspected, no changing its story. Monitor private randomness means the monitor uses its own secret dice for the tests so the AI can't predict them and can't cheat. Trusted logging keeps a permanent, unerasable record of everything. And deterministic tool replay means the monitor can rerun the AI's actions in a secure little sandbox just to make absolutely sure the results match up. So let's put it all together now. When you combine these three big ideas, the safe zone, the bouncer, and the trust contract, what you get is a really comprehensive safety system that is always, always on. And this leads to a super important point. See, a long series of actions that are all individually safe could still add up to a really unsafe outcome. CAST gets this, and it accounts for it by thinking about safety as a risk budget. The system gets a total, finite budget for acceptable risk over its entire lifetime. That budget can be spent in different ways, a tiny bit at each step, maybe more at the beginning. But once that budget is gone, it's gone. This is what prevents that death by a thousand cuts scenario, where tiny, acceptable risks slowly pile up into a total disaster.
Now, it's also really important to understand the scope here. The creators of CAST are super clear about this. This is a theory for digital systems. We're talking about things like financial modeling or scientific simulations. It is explicitly not designed for controlling physical robots or some hypothetical all-powerful superintelligence. This quote from the paper, I think, just nails it. The goal isn't to create a perfectly harmless AI. That might actually be impossible. No, the goal is to take that terrifying, unknown, unbounded risk and convert it into something that we can measure, that we can audit, and that we can actually control. And that leaves us with a pretty fascinating final question. Frameworks like CAST are still mostly theoretical, but they point to a future where we might not have to simply trust AI. We might actually be able to prove that it's safe. So if we can do that, what kind of problems could we finally solve?